Okay, in this video we're going to be looking at the waves review sheet, and I know it says chapters 12 to 23. We're going to take off the 23 part and just make it 12 through 16. We're going to start off with what is simple harmonic motion. We started thus off with, this was the link between forces and motion, and then we jumped into waves. But simple harmonic motion is simply defined as any motion that regularly repeats itself. Which means it's got to have the same time down, same time up. But if the motion happens over and over again, it's going to have the same thing when we get into talk like period, which is the time it takes for one vibration or oscillation. And then frequency, which is the number of vibrations per second. Okay. The other way we can think of simple harmonic motion too is that the amount of force and the amount of acceleration is directly proportional, or is proportional to the amount of displacement. So if we talk about a vibrating mass in a spring, the further it's outstretched, the more force it has going back up. Okay. All right, number 2. We attach a 3 kilogram mass to a spring, and it stretches that spring 5 centimeters. What's the spring constant of the spring? Now, this one you are definitely going to have to do. This is Hooke's law. In Hooke's law, we know we have a mass attached is equal to 3 kilograms, and the delta x, the amount of stretch, is going to be 5 centimeters. Now, remember, as soon as you see centimeters, you're going to be thinking, I got to change that over. So it's going to be 5 times 10 to the negative second meters. Okay. Now, the other thing we got to know here too is if we're talking about a mass on a spring, putting it down, here's my mass. The force it's pulling down is equal to the force due to gravity. So I have to go find the force due to gravity first. So it's going to be m times g. So it's going to be 3 times 9.81. So my force applied is 29.43 newtons. So using Hooke's law, F equals kx. The force is 29.43 newtons. My k is what I'm looking for, and the amount of stretch is 5 times 10 to the negative second meters. So I take my 29.43, divide that by 5 e neg 2, and I get 588.6 newtons per meter. Now that's what we're going to have to do for this. Okay. Now part B, if we set a simple harmonic motion, what's the frequency of the motion? This one I am not going to ask you to do on the quiz. Okay, just real quick though, what I would have to give you would be the period formula of a vibrating mass on a spring, which is 2 pi times the square root of m over k. And so what you would do is you take the mass, you divide it by our spring constant, that 588.6, take the square root, multiply by 2 pi, and that's going to give you the period. Once you know the period, frequency is 1 over the period from there. Okay, so again, I won't ask you to do B, but that's how you would do it if we were asked. Number 3, this comes straight from our lab. Okay, what happens to the period pendulum when the length is quadrupled? Okay, again, the equation I would have to give you would be T is equal to 2 pi times the square root of L over G. And now in this case, well, if I can just set it up, since we know that we can redo this and say that T is proportional to the square root of L. So since that's the only thing changing, this is the only relationship I'm looking at. So if I quadruple L, so if T was whatever it was times the square root of 1, that would give me something. But if I quadruple it, T times the square root of 4, the square root of 4 is going to be equal to 2. So if we quadruple the length, we're going to double the period. Okay, because it goes from 1 to 4. Okay, so this would be 1, that would be 2. Now our next one, next page. It asks about what is similar about the 2 types of mechanical waves and what's different about them. Okay, well the 2 types of mechanical waves are transverse and longitudinal. Remember, transverse, if the wave is traveling off to the right, the particle is going to vibrate perpendicular. So that's my wave motion. My particle motion, I'll put this in red, is going to be up and down. Longitudinal, remember if the wave travels off this way, We have compressions, expansions, compressions, expansions, compressions. In that case, our particle motion is going to be parallel. Okay, so that's different about them. Okay, the main types, though, so similar there. Both of these waves carry energy, and they require mediums to travel through. Okay, so similar is they carry energy and require a medium. To travel through. I mean, other similarities, they both have wavelengths, they both have frequencies, they both have amplitudes and stuff like that, okay? But the main difference is what happens to the particle motion as you go through. All right, number 5. Green light has a wavelength of 5.2 times 10 to the -7 meters with the frequency and period of the green light. Now, because we're talking about light, we know the speed. The speed of light is c, which is 3 times 10 to the 8th meters per second. And if we have a wavelength of 5.2 times 10 to the -7th meters, it means we can find the frequency by taking v equals f times lambda. So 3 times 10 to the 8th meters per second is equal to my frequency, that's what I'm looking for, times the 5.2 times 10 to the -7th meters. So if I crunch this in, it's going to be 3 times 10 to the 8th, so 3e8, divided by the 5.2 e -7, and that's going to give me a frequency of 5.77 times 10 to the 14th hertz. Now that's our frequency. If we want to find the period, my period is equal to 1 over the frequency. And so all I would do is take the 5.77 times 10 to the -14th, and I would raise that to the -1. Or do 1 divided by that. It's going to be the same thing. But my period is going to end up being 1.73 times 10 to the -15th seconds. So that's the amount of time it takes for one vibration or one oscillation. Number 6 says the sound wave travels 150 meters to a rock wall and then reflects back to the source. How much time passes before the echo is heard? Assume it's traveling through the air at STP. So since we're talking about sound traveling at STP, we can go to the front page of reference tables and find the speed of sound at STP to be 331 or 3.31 times 10 to the second. So 331 meters per second. We know the distance is 150 meters to get there, but then it's got to come back. So it's actually 150 meters times 2, because it's got to go there and back again. So our total distance is 300 meters, and we're looking for the time that it takes. This is our old school equation. So V is equal to D over T. So 331 meters per second is equal to the 300 meters divided by the time. So cross multiply that, and you're going to end up getting the T, or not room here, T is going to equal 300 over 331 meters in meters per second. So push that in the calculator, 300 divided by 331, and I'm going to get 0.906 seconds. So just a little under a second, 0.9 seconds. Okay, we move on to number 7. And number 7, we're not going to do it all. We completely dropped off all of the mirrors and lenses equations, so we don't have to do that at all. For number 8, polarization. Polarization, what you have to remember here is this is when we have little slits of Polaroids going through, and the light comes in like this. Remember, the light is vibrating in all directions. It's vibrating up and down. It's vibrating in and out like that. Okay, and only the light that's allowed to go through is the stuff that vibrates parallel to the slits. So if we were to put another Polaroid up here where the slits are perpendicular to that, then there's going to be no light coming out. Now, why is this important? This proves, and I'll put it here, this proves that light is a transverse wave. Okay, we assumed that light was a wave, but we didn't know if it was longitudinal or transverse. Polarization proves that it's transverse. Okay. Number 9, a person shines a light at a friend who's swimming underwater. If the ray in the water makes an angle of 36.2 degrees with the normal, what's the angle of incidence? All right, so if I draw a picture of this, okay, down here we have our water. Okay, we have a person shining the light coming in like this. Okay, remember we always measure our angles to the normal, so this is our theta 1 angle of incidence. Down here the ray is going to bend inside the water. So down here's our friend swimming. You get the idea. Okay, and now this angle to the normal is always 30, or in this case is 36.2 degrees. And this will be our theta 2. And now we can use Snell's law here. We can say that n1 sine theta 1 is equal to n2 sine theta 2. Because we're coming from air and we're going into water, n1 is 1, and we're looking for theta 1, and n2 is water. Now you can find this on the reference table. The index refraction of water is 1.33, and we have our sine of 36.2 degrees. And so if I crunch this in, I'll show you the calculator. What I'm going to do is I'm going to take the 1.33, I'm going to multiply that by the sine of 36.2 degrees, and I get that 0.7855. So for this I'm going to take the inverse sine, because this is equal to the sine of theta 1. I got to take the inverse sine, so second sine negative 1 of the 0.7, and I end up getting 51.8 degrees as my angle of incidence. That's the theta 1. Okay. Number 10, again, we're not doing any of the lens stuff, so this one's going to be completely gone. We don't have to worry about any of those equations. We're not going to do those. And we'll flip the page. Number 11, light moves from flint glass into the water at an angle of 28.7 degrees. We want to know what's the angle of refraction. And then at what angle would the light have to be incident to give an angle of refraction of 90 degrees, aka what's their critical angle? Okay, so we're going from flint glass. If you check on the reference table, flint glass has an N of 1.66, and water is 1.33. And so if I'm going from flint glass into water, I'm going to use Snell's law. So N1 sine theta 1 is equal to N2 sine theta 2. So 1.66 times the sine of 28.7 degrees, and that's going to equal 1.33 times the sine of theta 2. So pushing this into our calculator, you get 1.66 times the sine of 28.7 degrees. We're going to divide that by the 1.33, and that's going to equal 0.599. That's equal to sine of theta 2. So in order to get theta 2, I'm going to have to take the inverse sine of my answer of the 0.599, and that's going to give me an angle of 36.8 degrees. Now for part B, they want to know what angle would the light have to be to give an angle of refraction of 90. So all we're going to do is going to go Snell's law again. N1's still the 1.66, but now this time we're looking for theta 1, because that's going to be our critical angle. And now we've got 1.33 and the sine of 90 degrees. So this goes from theta 1 to theta sub c, because our theta 2 is 90 degrees when theta 1 is a critical angle. So we're going to crunch this back in again. So we've got 1.33 times the sine of 90, which is 1, and we divide that by 1.66, and we get 0.801. Now remember, this is equal to the sine of theta sub c, so we have to take the inverse sine of the 0.801, and we end up getting that the critical angle, theta sub c, is 53.2 degrees. Okay. Number 12. Now, what's the speed of light in sodium chloride? And I'm going to pause this for a second. Okay, so for 12, what's the speed of light in sodium chloride? Okay, so in our reference tables, the N, the index refraction of sodium chloride, is 1.54. Now, if I want to find the speed of light, I'm going to use the equation N is equal to C over V, where N is the index refraction of the substance, so in this case 1.54. C is our speed of light in a vacuum, 3 times 10 to the 8th meters per second, and we're going to solve for the speed inside the substance. So this is going to become 3E8, and we're going to divide that by 1.54, and we end up getting a speed of 1.95 times 10 to the 8th meters per second. A good way to remember this too, and a good mental check, is that anytime you go from air into any other substance, light has to slow down. Okay, so the speed of light always inside a substance is always going to be less than 3 times 10 to the 8th. Okay, they want to know what's the wavelength of light in air and in sodium chloride. So in order to find the wavelength, I'm going to use V is equal to frequency times the wavelength. Now they gave us the frequency, the 5 times 10 to the 14th, and we're going to use the speed. Then we're going to use the speed of light in air, which is 3 times 10 to the 8th, and then we're going to do that again using our speed inside sodium chloride. So I'm going to go the 3 times 10 to the 8th meters per second, because that's our speed of light in air, times the frequency, which is equal to 5 times 10 to the 14th, which is the frequency in hertz, and solve for the wavelength. And so my wavelength is 3E8 divided by 5E14, and I get 6 times 10 to the negative 7th meters. Now when I'm in sodium chloride, now my speed changes from 3 times 10 to the 8th to this 1.95. So I'm going to use V is equal to frequency times wavelength. So 1.95 times 10 to the 8th meters per second. That's equal to, the frequency doesn't change, so that's still the 5 times 10 to the 14th hertz. Solving for the wavelength. And so now my new wavelength, the 1.95 E8, divide that by the 5E14, and I get 3.9 times 10 to the negative 7th meters. Notice that the wavelength is less. When you go from one substance into another, if you go from air into any other substance, the wavelength is also going to decrease, just like the velocity. Number 13, what is diffraction? Diffraction is defined as the bending of a wave as it goes around a corner or through a slit. And the key difference here between diffraction and refraction is that with diffraction there is no change in speed. With refraction, there is. You have to change the substance, you have to change the speed, but with diffraction, there isn't. Now, we go to number 14. It asks for what is the wavelength of light that, when shown on a double slit, 0.5 meters apart, produces a second order fringe at an angle of 0.56 degrees. Now remember, this is another one. This is the one we did in lab just on Friday. I will be giving you this formula. So the formula you're looking at is d sine theta is equal to m lambda. And remember, this is what proved definitively that light is a wave. So if I want to do this, we're looking at d. D is the distance between the slits, so that's going to be your 0.5 millimeters. So I've got to change this to meters, though. So I've got 0.5 times 10 to the negative 3rd meters is my d. Okay, and I've got an angle of 0.56. So I'm going to go to the sine of 0.56 degrees, and that's going to equal to m times lambda. Because it wants the second order fringe, that is my m. So 2, and I'm looking for lambda. So really simply, I'm just going to plug this into my calculator. So I'm going to go 0.5 e neg 3, because I got to be in meters. And I'm going to multiply that by the sine of 0.56. And then I'm going to divide that by 2. And so I'm going to get, as an answer, 2.44 times 10 to the negative 6th meters. That's my wavelength. Okay. Now, all of the rest of these, 15, 16, 17, 18, 19, and 20, these are all in Chapter 23, and we are not going to do any of them. So this one is shot. So that ends our review sheet.